In this video, we will go back to a core concept in quantum mechanics, namely the wave function. We have discussed this in other videos, but now it is time to look at it in a bit more detail. In the introduction to quantum mechanics, we got introduced to the concept of what a wave function is. In short, it is a function which describes a quantum object like an electron, while encompassing the wave particle nature of it. In this video, we will look at some of the most important wave functions of quantum mechanics. We have of course already seen some wave functions when discussing quantum tunneling and the hydrogen atom, so these functions we will skip. If you're interested, you can watch the video about these topics. So without further ado, let's look at the Schrödinger equation and consider the relevant scenarios and figure out the relevant wave functions. One of the most important cases to consider is the harmonic oscillator. This potential is very important because in many cases one can approximate much more complicated situations with the harmonic oscillator. An example of a simple harmonic oscillator is a spring, and this has also led to the famous phrase, "everything is a spring," because many situations can be approximated in this way. Classically, we can write the equation of motion using Newtonian mechanics in the following way. F is equal to minus kx equal to m times the double derivative of x with respect to t, where k is the spring constant and m is the mass. The equation of motion has the following general solution, where x is equal to a sine omega t plus b cosine omega t, where omega is the frequency and a and b are some constants. We can also write the potential as V is equal to 1/2 k times x squared, where the angular frequency can be written as omega is equal to the square root of k over m. We will soon write the potential in a different way using the definition of the frequency. So far we have talked only about the classical situation, but we will see some similarities when trying to solve the quantum situation, so keep in mind the result of the classical problem. Now it is time to consider the quantum situation. To solve the quantum harmonic oscillator, we can first rewrite the potential in the following way, where V is equal to half m omega squared x squared, using the relation presented earlier. This form is more convenient when we will solve the time-independent Schrödinger equation, which is written as minus h bar over 2m times the double derivative of psi with respect to x plus half m omega squared x squared times psi is equal to e psi, where we now have plugged in the potential into the equation. Now we have defined the problem which we need to solve, and actually there are a few ways to solve this problem, so maybe you have seen some other version of it, but don't worry, the result is the same. In this video we consider the algebraic solution to the quantum harmonic oscillator. This solution is a bit more neat, but relies on more complex operators. I introduced operators in the video about the uncertainty principle, so please watch that if you want an introduction to operators, because we will build on the knowledge from that video. By looking carefully at the Schrödinger equation, one can see that it is possible to rewrite it in a more suggestive form, where we write 1 over 2m times p plus m omega x squared, and then everything times psi is equal to e psi, where p is now the momentum operator. In general, this entire term on the left can be considered as the Hamiltonian of the system. As we discussed in a previous video, the situation is a bit complicated because we are dealing with operators. To resolve this issue, we can define the ladder operators, where the ladder operator a hat plus minus is defined as 1 over the square root of 2h bar m omega, and then that times the minus plus ip plus m omega x. The plus sign is the raising operator and the negative sign is the lowering operator. So there are two. It turns out that the raising operator increases the energy of the system and the other decreases the energy of the system. Very convenient. Sparing you from the ugly math, it turns out that using these operators we can rewrite the Schrödinger equation in terms of these operators, where we write that h bar times omega and then in parentheses one letter operator times the other letter operator plus minus 1/2, and then everything multiplied by psi is equal to E psi. In this form it is rather straightforward to solve the Schrödinger equation. Firstly, in this new form we can easily read off what are the energies of this system. The product of letter operators just represent the energy level, so we can write the energy as simply E of state n is equal to h bar omega, and then in parentheses n plus 1/2, where n is the energy level and n0 is the ground state. If you go back and look at the Schrödinger equation, it is clear that this comes straight from reading the Schrödinger equation. We can also solve the Schrödinger equation, and we then find that the ground state is given by the wave function, where psi naught, the ground state, is equal to m omega divided by pi h bar to the power of 1/4 times e to the power of minus m omega divided by 2h bar and then times x squared. The nice thing about using the algebraic method with the letter operators is that using the ground state wave function we can easily find the wave function of any other state using the general wave function of the harmonic oscillator. So psi of any state is equal to 1/n factorial times the erasing operator a hat plus to the power of n, and then times the ground state wave function psi naught. So we simply just add the letter operators to obtain the wave function for any higher state, and the fraction in the front is just the normalization constant. And that concludes our look at the harmonic oscillator and its wave function. Now we can move on to consider the free particle. We are simply asking, how does the wave function look if there is no potential? And we consider a free particle. In the classical world, we just have a particle with a well-defined position and constant momentum. This should be a rather simple situation, but things are different in quantum mechanics, as we will see. Since the potential is 0, the Schrödinger equation becomes minus h bar over 2m times the double derivative of psi with respect to x is equal to E psi. And we can actually make it look a bit more like the classical equation of a spring by defining k such that k is equal to the square root of 2me divided by h bar. And this allows us to rewrite the Schrödinger equation as the double derivative of psi with respect to x is equal to minus k squared times psi. In this form it is just like the equation of motion of the classical spring. How interesting. This means we already know the solution, which is psi of x is equal to a times e to the power of ikx plus b times e to the power of minus ikx, which is equivalent to the sine and cosine solution presented earlier, but this form is more instructive. Now it appears as if we have solved this problem. There's just one small problem with a stationary free particle. Because of the uncertainty principle, there's no such thing as a free particle with a definite energy. Thus this stationary solution is not normalizable. So what if we want to solve the time-dependent Schrödinger equation? Well, this turns out to be rather complicated, but it is normalizable for some wave number k. The solution is rather complicated, but the wave function becomes psi of x and t is equal to 1 over square root of 2 pi times the integral from minus infinity to plus infinity of the phi function with respect to k times e to the power of I and then parenthesis kx minus h bar k squared divided by 2m times t, and then integrating with respect to k, where we now have this phi function of the wave number. This has the form of an integral, and it is normalizable as we now consider a wave packet. This phi function is defined in terms of the stationary wave function, where phi of k is equal to 1 over the square root of 2 pi times the integral from minus infinity to infinity of psi with t0 times e to the power of minus ikx, and the integral is with respect to x. And I know this looks rather complicated, and it is, but this is a great example of how considering something as simple as a free particle can turn out to be rather complicated in quantum mechanics. I hope the math didn't scare people away, I think the results in this video are very important, as the harmonic oscillator is one of the most important objects to study in quantum mechanics. Furthermore, the study of the free particle tells us something instructive about the unusual nature of quantum mechanics. This video builds on the concept from other videos, and if you want to see more solutions and wave functions related to different problems, then I suggest you watch the video on quantum tunneling or the atomic structure and the hydrogen atom. If you like this video, please comment, like and subscribe. If you want to donate to me, you can buy me a coffee using the link below. Stay tuned for the next video.